My name is Ms. Ho and I am a physics teacher. In this video, we are going to be learning what thermal equilibrium is and how it occurs. For those of you who are not familiar with the way I teach, I'm more of a whiteboard slash blackboard slash chalkboard kind of teacher. I'm not so much of a PowerPoint or presentation teacher, and that's why for online lessons I like to use the Jamboard. And the reason for this is because I like to scribble as I'm teaching, and I feel that as you are following the way that I scribble and explain, you'll be able to follow my thought processes and in turn build your own logical thinking processes to help you understand and recall the concepts better. So, let's look into what is thermal equilibrium. Now, before we get into that, first things first, we need to understand the difference between heat and temperature. A lot of people think that they're the same thing, but they're not. They are related, but they're not the same. So let's recall first what heat and temperature are. Heat is a type of energy, correct? So which means that it is measured in the unit joule. Whereas temperature is a measurement of how hot an object is. So the unit is in Kelvin. Let me just expand this a little bit. But this is not a unit that we commonly use on a daily basis. So in fact, we actually use degrees Celsius, and in some countries they use degrees Fahrenheit. Now, in terms of the definitions, heat and temperature, there are actually many ways to define them, but for this video, I'll just go through a few of the most common ones. So heat is broadly defined as the energy that is transferred between objects with different temperatures. Now this should make sense because with different temperatures there will be heat flow. So if you have something that's hotter than another, then yes, there will be heat flow from the hotter object to the colder object. In fact, that's also another way to define heat. It is energy that flows from a hotter object to a colder one. Put it this way, hotter to colder object. Temperature, on the other hand, is the measurement of how hot an object is and can also be defined as the degree of hotness. Now, another way to compare the definitions of heat and temperature could be could be based on the kinetic energy possessed. So heat is the total kinetic energy of particles in an object. Temperature, on the other hand, is the average kinetic energy of particles in an object. Now let me elaborate on this kinetic energy definition a little bit. Now, you can't drop the term particles and just say, oh, heat is the total kinetic energy in an object, or temperature is the average kinetic energy in an object. That's not true. Because what is kinetic energy? Kinetic energy is the energy possessed by a moving object. So if you see an object actually moving, that energy that's making it move, the motion energy, that's the kinetic energy. Now, that kind of energy is more of an external energy, so it is an external motion by the object. So that kinetic energy cannot be heat or temperature. It is the amount of energy due to the motion of the object when it's actually moving. In this case, this kinetic energy of heat and temperature refer to the internal energy of the particles in an object. So I'm just going to remove this because it's not true. Okay? So when we say kinetic energy, what does this mean? This comes back to our understanding of the kinetic theory of matter. So let's just go through a little bit about the kinetic theory of matter. So the kinetic theory of matter states what? Let me just make this a little bit bigger. Yeah. So what does the kinetic theory of matter state? It states that matter is made up of tiny, discrete particles that are constantly in motion, whether in vibration, translation, or rotation. Let me just expand this. Jamboard has a tendency to do that. Squash the words like that. So this is the kinetic theory of matter. So what does this mean? So I'm just going to come up with a simple illustration here just for your understanding. So let's say this is a representation of an object, of matter. And let's say we've got, we observe what's inside the matter here, and it's made up of a lot of tiny discrete particles. So I'm just going to do a very simple sketch here. So imagine that these are all the particles that exist inside this particular piece of matter. Say it's a solid. Now, we know that if the solid is not moving, there is no external kinetic energy. But that doesn't mean that the particles are not moving. As we already know from the kinetic theory of matter, every particle here is actually moving. So if it's a solid, they are vibrating in place. This vibration that each particle has contributes to its own kinetic energy. So we come back to the definitions that I have written here. The kinetic energy written here refers to that vibrational kinetic energy that each of those particles have. So heat energy refers to the total kinetic energy of the particles in an object, while the temperature refers to the average kinetic energy of the particles in the object. I'm just going to draw two objects here now side by side for your comparison. Let's say we have two objects made of the same material, but one is larger than the other. So logically, this of course has more particles compared to the smaller one. So when we talk about the kinetic energy, and this should make sense, temperature refers to the average kinetic energy of the particles. Whoops, I wanted to use the highlighter tool. Okay, it's the average. So when you think about the particle then, this particle and this particle, they'll have the same average kinetic energy because they have the same vibrational energy. So if they're the same, therefore they have the same temperature. But when you look at these two, yes, they can have the same temperature, but because they have different masses, obviously this larger object would have more heat energy. And when you look at the definition now, it should make sense because heat refers to the total. So looking at all the particles that exist inside those individual objects, there are less atoms here, so less overall total kinetic energy, hence less heat. While the larger one, there are more particles, so overall more total kinetic energy, therefore more heat energy. So now that we understand the difference between heat and temperature, it will enable us to understand more about the heat concepts. Now let's go into what thermal equilibrium actually is. So on this slide here, we have two objects. Now, whether they have the same material or the same mass, it doesn't matter. I just want you to think about the comparisons in terms of the temperature. So say the red color object is hot, the hotter, and the blue color one is colder. I'm just going to write it as cold. Now we place them side by side, and I want you to think, okay, now they've got different levels of, heat energy, right, for each particle. So there will be transfer of heat energy. So in which direction does the heat move? From the hot to cold or cold to hot? Correct. So you'll find that most of the heat energy, I'm just going to put a different color here just so that it's easier to see. You'll find that heat will be moving from the hot to the cold object. Now, do you think there's any heat energy being transferred from the cold to the hot? Actually, there is. But it's a lot less. I'm just going to flip it. Yeah. It's a lot less. There is. There is still heat energy being transferred. Now, a lot of books, websites, and a lot of texts may tell you that there's only heat transfer from hot to cold and not from cold to hot. That's not true. There's actually heat transfer going both ways. It's just that there is more heat energy moving from the hot to the cold. So how it would describe this overall is to compare the net transfer of heat. Net here refers to taking whatever that needs to be added, and we deduct whatever needs to be subtracted, and we're left with the balance. So in this case, let's look at the higher value of heat and deduct the lower value of heat. That means we take the bigger arrow deduct the smaller arrow, and you find that there will be a net transfer of heat from the hot to the cold object. So here, let me write that down, there is a net transfer of heat from hot to cold. Now this is not thermal equilibrium yet, but what we will find is that as heat is being transferred, the hot object loses heat energy and the cold object gains heat energy. As the temperature gradient decreases, temperature gradient here refers to the temperature difference. As the temperature gradient decreases, there will be less and less heat energy being transferred from the hot to cold and more heat energy being transferred from the cold to hot, until they reach a situation where, oops, let me change that color, until they both become equal. So at this stage, there will be heat transfer in both directions, but the value of the net transfer of heat is 0. So I'm going to write that down. The net transfer of heat is 0. That means the rate of transfer is equal. Let me just expand this a little bit and change the color. And at this stage, you should also be aware they have both the same temperature. Now I'm aware that I've left this in red and blue. The colors are already the same, but I'm leaving the object colors here as such so that you know which is the original object. Now, just to point out to you, the term net is extremely important because the word net here refers to the balance. You know, like I said, you add what needs to be added and you deduct whatever needs to be subtracted. Okay, the net transfer of heat here is 0, but the rate of transfer is equal. If you drop the word net, it would be incorrect. If you just wrote transfer of heat is 0, that's wrong because you're saying there's no heat transfer at all. But that's not true. There's heat transfer in both directions. It's just that after deducting whatever, the net value is 0. So what is thermal equilibrium? Thermal equilibrium refers to this situation. Equilibrium, you must remember, in physics means balance. That means, for example, in this case, the heat or temperature is balanced. So thermal equilibrium is the concept where objects in thermal contact, it could be 2 or more, have 0 net transfer of heat and have the same temperature. That's what thermal equilibrium is. So remember that for thermal equilibrium, there are 2 conditions. Both objects must be in such a situation that the net transfer of heat is 0 and they're both having the same temperature. So again, just to remind you, the first diagram here, that is not thermal equilibrium. This first diagram is just to show you how heat is transferred and what a hot object. So the first diagram here does not show you thermal equilibrium. It just shows you how the heat is transferred, how the hot object loses heat energy and how the cold object gains heat energy. And this happens until thermal equilibrium is achieved, which is what we see on the right hand side, where the net transfer of heat is 0 and both objects have the same temperature. So once we understand how thermal equilibrium works, we can use this to our advantage in our daily life. For example, how a baking oven works to bake. The baking oven would of course produce a lot of hot air. When you put the batter in there, the hot air will transfer heat energy to whatever that you are baking, and that's how the baked goods become hot and can get cooked or get baked. This is also how thermometers work. By placing a thermometer in contact with the human body, for example, under your tongue, in your ear, or in your butt, that's how the thermometer is able to match the same temperature as the human body and give you the temperature of the patient. This is also how fridges work. By placing food inside the refrigerator, the cold air opposite to the baking oven now draws heat away from the objects, keeping them cool and maintaining the freshness for a longer time because it reduces the bacteria activity. Also, how you can make hot drinks become colder, you can either add cold milk, cold water, or even better, add ice. And with the exchange of heat energy between the hot and cold liquids or solids, that's how the temperature of the hot drink can be decreased. This is also how cooling pads or even heating pads work. By placing a cooling pad on the injured area, this draws heat away from the body and reduces the swelling. Alternatively, you can also use a heating pad, which in turn would provide heat to the affected area to speed up the healing process. So this concludes my video lesson on thermal equilibrium, and I hope you have found this video educational and helpful. Don't forget to click like and remember to subscribe to my YouTube channel, Physics Rocks. Happy studying!